comenzar, darle la bienvenida a todos, a todas. Muchas gracias por su tiempo, por su participación en este webinar. Y bueno, el día de hoy, justamente como está aquí en la presentación, vamos a hablar un poco sobre los sensores de fuerza piezoeléctricos, en donde Nicolás va a partir con una breve introducción, presentando a Varitec, un poco lo que hacemos. Después va a hablar Carmín, y él va a entrar un poquito más en detalle en lo que es el tema. Y después para finalizar, ahí Nicolás va a terminar con una demostración. Y después viene una sesión de preguntas en donde todos habrá un espacio donde todos pueden hacer sus respectivas consultas. Así que espero lo disfruten, espero les saquen el máximo provecho y después puedan hacer no sé, todas las preguntas que vayan quedando. Así que, bueno, ahí el tema del inglés, ahí Carmín va a hablar en inglés, pero sin embargo después en la sesión de preguntas igual pueden hablarlo en español, pueden hacer la pregunta en español. Carmín igual entiende un poco el español y si no, ahí Nicolás también lo puede ayudar en la traducción. Así que eso, Nicolás, gracias por tu tiempo y ahí ya te doy el paso ahí para que comiences.
Muchas gracias, Benjamín. ¿Está bien esto? Sí. Bueno, de nuevo, ahí agradecerles por estar aquí. Me presento. Soy Nicolás Fernández, de la empresa Varitec. Somos un proveedor de soluciones en tecnologías predictivas, fundado en el año 98. Yo me encargo de la parte de investigación y desarrollo, y trabajo también en la parte dedicada a atender requerimientos y a realizar proyectos dentro del área académica y de consultoría, más que en el área minera, que es la principal en realidad parte en la cual opera Varitec. Somos una empresa fundada en el año 98 enfocada en manutención predictiva, enfocada en sensores piezoeléctricos y en monitoreo predictivo a través de vibración principalmente. Somos desde el año 2000 un integrador de Entec IRD y Rockwell Automation para su línea de monitoreo de condiciones, y desde el año 2008 que nosotros trabajamos acá en Chile la marca PCB Piezotronics. PCB Piezotronics, vamos ahí a ver una presentación, la presentación de hoy día está dictada por Carmín Solzano, parte de esta organización, y bueno, le agradezco mucho esta oportunidad en la cual estamos realizando esta serie de webinars para aprovechar de difundir como, las distintas tecnicalidades de distintos tipos de sensores que provee PCB. Y bueno, nosotros como el distribuidor acá ofrecemos servicio de venta, de asesoría en selección, trabajamos equipos demo, trabajamos temas de capacitaciones, garantía y cosas acá. O sea, tratamos de hacer que la experiencia de PCB, de usar PCB en Chile sea lo más cercano a usarlo en Estados Unidos o en otros países. También somos un integrador de sistemas de monitoreo de condiciones, bueno, de Rockwell, y también trabajamos en las marcas aquí principalmente de Divisoft, Sensotec y RD Balancing. Bueno, como empresa tenemos alrededor de 50 personas, trabajamos aquí en Santiago y en Calama. Trabajamos con una cultura de daño cero, enfocándonos en alta seguridad en las soluciones que implementamos en terreno. Pero para bajar un poco la parte más técnica, nosotros las marcas que trabajamos e integramos son aquí, PCB Piezotronics y Entornos, son el área más potente en lo que es instrumentación, en lo que es monitoreo industrial y en lo que es investigación y desarrollo. Complementamos esta solución con sistemas de adquisición de Divisoft y también podemos aportar sistemas de calibración de Modal, que es una división dedicada a sistemas de calibración, a sistemas en general dentro del PCB Piezotronics. Esa es como una mirada general dentro de las cosas que que trabajamos como empresa. Y bueno, el webinar de hoy se enfoca en uno de los tipos de sensores específicos dentro del catálogo de PCB. Anteriormente, el primero de estos se enfocó en acercamientos piezoeléctricos, después nos enfocamos en micrófonos, ahora vamos a sensores de fuerza y bueno, más adelante vamos a ir viendo ya vamos a ir viendo aplicaciones más específicas de estos sensores, como análisis modal o mediciones en ambientes ya específicos como se dice, mejores prácticas en terreno y cosas en webinar futuro. Bueno, dicho esto, de nuevo agradecerle su presencia y darle aquí el pase a Carmine Salzano. Lo estaba compartiendo pantalla.
Muchas gracias, Nicolás. Buenos días a todos. No hablo español, me entiendo. So let's start with the sharing my screen. I hope you can hear me very well, right? Hope so. Hi, Nicolás.
We can hear you well.
Okay.
Agregar ahí que cualquier pregunta en español o inglés podemos hacer de interlocutor y que...
Sí.
Yeah. I will, if something happen or if I speak too fast, Nicholas, please stop me, okay? Or if any problem. Okay. So today, piezoelectric force sensor. And the agenda is very short. It's just 2 points, which means one, once we will explain the force sensor technology, how they are designed and work and specification. And then we see some example, some really practical example. After that, Nicholas will show a short demo, but very interesting. And after that conclusion, we have preguntas, which means your questions to me. You can speak slowly Spanish and habla español lentamente, entiendo. And I can unfortunately reply only in English. Okay, so we can start the agenda, Nicholas.
Yeah, we can hear you well.
Okay, so the first point is, first of all, Nicholas mentioned about the application of the force sensor for modal test. Well, I will not speak about modal test application because it's very common that use a force sensor to measure the force, and then the results you measure with the response of the structure you measure with an accelerometer. That's very clear, but the force sensor, they have a different shape, also different specification, and many different application. Therefore, it is not only for modal tests, but there are many other applications, not only for testing, like a drop test, shock test, or even a satellite, but also for process monitoring to measure, for instance, the tooling effect. So there are a lot of application. Of course, I will not go to details, but the second part of the presentation, I will show some real example of application covered by paper, which you can find on the website. While this presentation, at the end, I will send to Nicholas. So please make sure to send your email to Nicholas and you will receive my presentation. Right, Nicholas?
Ya, tenemos esta presentación se les va a hacer llegar y sus correos en realidad ya los tenemos ahí en el listado de asistentes. Si no pudieron asistir, también les va a llegar.
Yeah, you can see from now already 2 different ships. A very general purposes. I hope you can see my mouse cursor. It's a very general one. And this is the ring style triaxial. So it seems different, but they are both force sensor for different use, of course, a specification. Piezoelectric. The difference is that we have 2 technology. One is piezoelectric for force sensor, so purely dynamic force sensor. The other one is a strain gauge technology for load cell, but these are purely for static. And Nicholas, after a show, we show both. We manufacture both sensors. I repeat, piezoelectric for purely dynamic force, which is today we will discuss. So the difference you will see is very different. I will discuss the stiffness later, but you can see pretty much the quartz ball where we cut and we build up our sensor. And the sensor is always built on the principle of quartz effect, which means any silicon dioxide, when it's subjected to a force, you will have a different polarization of the asymmetric lattice under load, and therefore you will have a charge output. This charge output, you don't have to imagine that you have a very big change in the structure, or you will see a structure will move. These sensors are very stiff. You will not see any movement. But the principle is that always Newton's force, because you have a mass time acceleration, so you will measure also, you can measure also this on this base. The force sensor, how is designed? is a very stiff metal, and then inside the heart of the sensor is a crystal, which is like quartz, for instance, and electrode. Electrode because the electrode will collect all the charge accumulated on the surface of the piezoelectric material. You can imagine a very slight quartz of crystal. And then the output here, at this point, is a picocoulomb per Newton. So it's a dynamic force output, but in charge. However, if you use a MOSFET inside, a microelectronic, with this microelectronic, we transform the high impedance charge output due to millivolt, so voltage output, which is very easy to handle, not only with the data acquisition, but also using a very long signal. So very common today. But we still manufacture both units, both types, charge output and ICP or IP output. You can see a better picture. This is a real one. The 208 series is one of the most common. You will see it's very small, very practical, very wide application because you don't need a preload. Preload is an advanced situation where I will explain when I talk about ring style. So this is simply glue and mount, stud mount, and glue and measure. It's made of, you can see the preload, the crystal stack is here. I show you before. This is a real picture. You can see how small is it, and then you have just the thread to mount properly, either the cap, because this can use also for impact, or eventually to mount on a structure, and below you can mount the stinger connected to the shaker in case of modal analysis. And then you can see the microelectronic. This microelectronic transform the charge output to voltage output before good to go to the connector output. Specification as any other piezoelectric sensor, I would say any other sensor, the sensitivity is the most important parameter because it gives you how many millivolt you will have for each Newton or kilonewton output. Therefore, based on the 5 volt, which is a typical output voltage of force sensor, you will see automatically the measurement range in compression and tension because most of the sensor can use both. Of course, to use tension, you need a particular application for both base and top mounting in order to measure also the tension. What is it, the maximum static? Well, remember that the dynamic force, the compression measurement range is just dynamic portion. You will not measure any static with this sensor. So the maximum static is the sum of static plus dynamic. Why we need this one? Because even if the sensor measure up to 10 pounds, it can resist up to 60 pounds, even without measuring. But this is very important to not go above this because of otherwise the sensor will break, even if has a huge stiffness compared, for instance, to load cell static. And then, of course, the typical low frequency, high frequency. The high frequency is depending on typically the structure of the sensor. Why so high frequency range compared to load cell? Because it's a stiffness much higher in terms of design. However, the low frequency depend on the amplifier, the electronic. The electronic can be outside if it's a charge output sensor, is inside if it's an ICP, of course. And the ICP, in this case, the low frequency response is fixed. The rest is something that can be very easy. The discharge time constant is a parameter very important in all ICP as sensor, accelerometer for sensor and pressure sensor and so on. Because it gives you how much time the signal takes to completely, we'll say 37% of discharge of the original value. So very important to define how much it can keep the static. Okay, in this case, the static can keep it for, let's say, 50 seconds, but this is to discharge 37% of the time. So I already mentioned that range time sensitivity that is defined at 5 volt. So once you have the sensitivity, just dividing by the output, you will see the range, which is simply 5 volt divided sensitivity. So it's also fixed, especially for the ICP force sensor. Resolution, what is it? It's a minimum level that is able to measure. So of course you want to stay a little bit above the resolution in order to not measure the mud so the noise. But anyway, the resolution, the maximum range, I would say the range, define the dynamic of the sensor, which is very, very broad, like any other piezoelectric sensor. Also, linearity is important because define the, I would say, the accuracy, which means that when you increase the level, you will stay in this bandwidth, and so the sensor has only 1% of full scale linearity, which means it's very close to the straight line, and this ensures also the very, very precise measurement of this sensor. I already explained the response, the resonance define also the maximum frequency, because once we define the frequency, we can say 20% is the highest frequency you can measure. But of course, all these parameters you can find in the specification, so you don't have to worry. Also, the charge time is connected to the low frequency response is purely the response, typical response of any filter which is not straight. So the frequency response is where the curve is flat. Where it's flat, of course, you have the same sensitivity in any frequency range. So this is a frequency range of working of the sensor. Now let's go to some specific force sensor, because so far what I said so far is pretty much is for any piezoelectric accelerometer, force sensor, or pressure sensor. Now the application, the mounting is slightly different. First of all, you need to have very close mounting base, like for accelerometer. But in this case, eventually, sometimes you want to mount also like a pancake between two plates, because in this case, you want to mount to measure also the tension, not only the compression. So of course, you need to a particular application. But before to look at this, look at the calibration. So every single sensor is calibrated. It's calibrated like any other PCB sensor with the linearity and also specific sensitivity. Now, let's finally see the ranges. We have different type of shapes. This is very important because you will see the also you can guess which is the different application we can apply. First of all, I already repeated, 208 is the most I would say widely used because it's small, because you don't need a particular care to mounting. Of course, you need a flat mounting surface, but it's very small and very high frequency range. And you can see, of course, the CO1, CO2, CO3 with a different sensitivity, therefore different ranges in terms of newtons, in terms of force. But sometimes you need to impact the sensor to measure the impact force. In this case, you can see this sensor has a cap. This cap is different from this one. It's much robust because in this case, the cap can resist to much 5,000 pounds, but even 50,000 pounds. So very high. So you can hit with a hammer. You can hit very strongly the impact cap, which protect the sensor for breakage. Because even if the stiffness is high, you need to protect also the damage if it's a metal-to-metal impact. Then we have another sensor, which is a ring style. The mounting of this one is slightly different from the previous one, because the ring style, you need a preload. Why? You need to mount like a pancake between two plates. And then between you have a stud. We supply the stud, and the stud is calibrated with the sensor, because in order to ensure linearity, you need to a certain preload. So you have you tighten the torque, the sensor, the stud, between the two plates in order to the sensor is fixed between these two plates. In this way, we call preload. And we define how much preload we need to give to this force sensor. If, well, of course, we have a procedure for preloading properly the sensor between these two plates. Only the ring style sensor, this one. This is single axis. But of course, if you want to avoid the preload, then you can buy a sensor, which is the same, you can see here, but preloaded between two, I would say, two plates, okay, two interface ring. The same is for triaxial. These are triaxial ICP, which is also available in charge output, and triaxial with a 4-pin connector with the 3 axis, so X, Y, zeta, and this one has a stud, which is calibrated together. If you want to use your stud, you should ship to PCB for calibrating. However, mounting with its own stud between two plates, you need a preload. Again, preload procedure. Otherwise, you can see the sensor is the same between the two plates already preloaded. You don't need to do anything else in this case. Of course, you need to accept the sensor is slightly taller. Okay, I hope I give you a little insight about some different shapes of the force sensor. So force sensor can measure the tip of a shrimp, just to give an idea, up to the very shock and parashock impact. So we have a different type of piezoelectric force sensor. Of course, the conditioner, for instance, in this case, you can go directly with the Duvasoft, for instance, data acquisition, but honestly, you can also use a DC coupled conditioning node only for preloading, because preload is a purely static operation in order to ensure that ring style model is preloaded. That's another convenience to use when it's possible, the 208 series, which does not need preload. And the application, of course, I have no time to, because also I want to have your questions. So I have no time to explain all the possible application with this sensor. So I selected a couple of applications which are covered by papers which you can find on the website. And you can read yourself in any application, aerospace, automotive, or any general test, even material testing, drop test, quality control, component test, you can use a force sensor to measure the actual dynamic force on the sensor. But it's not only dynamic. For a few seconds, you can keep also the static with this sensor, because the a microelectronic inside the sensor has a long RC circuit. So the DTC is very long. So you keep it static for a certain while. But of course, not like a load cell. And Nicholas, right after, will show you this simple demonstration. So let's start with the final part of my presentation. And I really apologize if I've spoken too fast, but let me know, Nicholas, is so far is too fast?
Yeah, it's okay. I think it maybe a bit slower. It's better. But,
okay.
But we can.
Okay. I will slow now during the presentation of the two cases before conclusion, my conclusion. First of all, this is a car door, right? Lock. You can see these are mechanisms to use to lock the door of the car. So very common. And of course, what you want to measure? You want to measure the force during locking, right? To open and close the door of the car. You can see here a very simple 208 mounted in this beam here in order to measure the force of tension and compression during door lock actuators working. This is good, but at the point you can see why we don't use a strain gauge static load cell, which is also a little bit dynamic. Well, let's put up a comparison of different parameters of the technology advantage between strain gauge and piezoelectric. So force sensor, piezoelectric, and load cell strain gauge. First of all, there's no comparison about stiffness. Stiffness much higher in piezoelectric. Like also dynamic response, of course, is very high. So I don't want to go through all this. You can see even the range is very high. Sensitivity is very high. So temperature effect, everything is higher. Where is the only bad point of piezoelectric? Of course, is static. Because if you want to have a purely true static, then of course you need a load cell. But load cell is much bigger than the other one. Let's also compare the tip in this case to see the frequency, okay? This is an impact tip. You can see it is very big here. Another tip here to the force sensor on a mounting base. So first of all, you can see here the load cell and here the force sensor, okay? Two types manufactured by PCB. Which is the meaning of this test? This test is to, first of all, to check it out, the frequency range. Well, this is load cell. You can see the first mode, the first resonance is around 36, few hertz. You can see 2 hertz, 2.5, okay, the resonance. However, the force sensor, the first mode, is around 36 kilohertz and more. So you can see immediately the frequency range difference. Here you can use for few hertz, very few hertz. This one you can use tens of hertz. So very different level of things, of frequency response. Now we can see, however, the static response in this case. As you can see here, the discharge time constant is how much it can keep the static. You can see they are both the same range of Newton. You can see same Newton. The stiffness, is different. The mass is also different, and of course the frequency. But if you have an event which is quite small, short, the sensor is able to measure very short event, slightly bigger, because the DTC is 500 seconds in this case. Okay, and then you have the steady load. Steady load is a load cell, only if you want to use, in this case, load cell. Let's see the comparison, and this is one of the most important reasons why in this case, for this kind of application, you cannot mount a load cell because it's too big. Okay, therefore you can see the sides. There is no comparison, right? So for this application, absolutely you cannot mount this load cell. Okay, and also this is a final remarks regarding the frequency. So when you want to measure up to 0.5 hertz or below, very close to 0 hertz, strain gauge technology, so load cell is the only choice. When you want to measure from 30 hertz up to any kilohertz, then of course piezoelectric sensor is the only hope. When it's between 0.5 hertz and 30 hertz in this gray region, then of course this is an overlap, which means eventually you can use both. Okay, but in this case, of course, there are other questions like dynamic range, like the sites, and so on. So in this case, you can make a comparison in this range. Okay, that's the first point. I don't know, Nicolas, if I was speaking slowly, if I can stop for a second to wait for your question eventually. I don't know. Let me know. Let me know.
Hello, Carmine. I think it's
Yes.
good speed.
Before to go to the last case study,
Yeah.
there is any question? Or you want to prefer to stop question when at the end, okay?
Sí, I think es mejor
Okay.
al final.
Mm-hmm. Okay. So, is okay the speed?
Yes, yes.
Okay. Now, the second one is an example's impacted drop. Again, in the automotive world, you can see this is a bumper test. It's a bumper in a machine. You can see this machine. The cross set here is equipped with the four force rings. Okay, force ring, probably you remember, we need a preload between two plates. Like this case, you can see 1, 2, 3, 4 sensors between two plates. In this case, what we built a force plate inside this cross head. Now the cross head mounting the machine hit the bumper. Okay, the bumper you can find on the highway or whatever, right? Hit the bumper. So it's very important to test the bumper to see if it resists to the crash of the car, right? So you can see the bumper in this impact. So and is measured by this force plate. Why force plate with the 4 each sensor? Because the level is very high. However, mounting 4, you can multiply the range of one sensor by 4, and you can see the sensor and the total energy. So which was the choice? The choice was this sensor, just because you can mount in a force plate with the 4 units. You can see 3, of course, because the other one is the other side. Mounting each one in a corner of 4 square plates. And of course was choosing this sensor here, 203B, for the ranges. okay? The impact range. So the range of 203 is like 90 kilonewton times 4, because you use a 4 in this kind of plate, and the plate is mounting inside the crosshead. So everything is subjected to impact, and the impact spread all over the plate and equally excite all the force sensor at the same time. That's the concept of force plate. Probably you can see better here. You can see the force 4 plates. Now you can see something different, because of course the F in X in the 3 direction, X, Y, zeta, you can measure, okay? Simply online or offline. It's very interesting because in this case you can measure the total force in the 3 axes. But look at this, you can measure also the moment. Yeah, because if you multiply the force in this direction times the distance where you mount the sensor, then you can measure the force. Okay, that's a formula. So the very interesting things in this force plate is that you can measure the total force in the 3 axes and the total moments in the 3 axes. So you can see how it's important not only for impact, but for any other application. Okay, now we go to keeping this concept. Now we go to the satellite test. I will go very quickly, but here in the satellite, you want to notch, you want to make sure you do not overstress the satellite, otherwise you damage the satellite, and you know the problem. So it's not enough to notch only the feedback through the accelerometer, but also you want through the force sensor. You can see here, charge output and ICP output tracks a force sensor, ring and link. You can see that without any plates, you can measure directly on the force on the component bolt. However, here you have 2 plates prepared by the customer, and it's spread all over the total force. It divided that single sensor, of course, in order to achieve the wanted total force. Again, you can see the familiar now total force and total moment calculation. Sometimes you can do in real time. Okay, I would like to take a break before conclusion to show you a unique sensor. I know this is not a force sensor, but when you deal with the force sensor, sometimes you need a strain gauge, foil strain gauge, to measure the strain. But in this case, the strain gauge you cannot dismount. However, this is the only reusable strain gauge. You can see a force plate, quartz plate with the ICP. So ICP output. You can simply glue with this glue. You can see the picture of the sensor inside, and is the only reusable strain sensor in the world with the high frequency. Of course, it's a purely dynamic, but very high frequency and very high sensitivity. This is an application here on mounting on a snowboard on ice, where of course you cannot mount any strain gauge foil. However, it mounted these gauges to mount during snowboarding. Another application is in the civil construction. You can see the different sides between the foil strain gauge and the actual, the only reusable strain gauge. Mounting on 2 different pillars, it's very easy to discover pure axial loading and axial plus bending loading on 2 different columns in the civil construction work. But as a final example, very quick, because I have a dedicated presentation for this sensor application, is on a hot boiler, where you cannot mount 80 degrees Celsius during operation. You cannot mount a foil strain gauge. However, the sensor is able to define not only the good direction at the bed boiler, but also the frequency in order to see also this parameter compared to accelerometer. Okay, I conclude my presentation. I thank you so much, and I'm sorry if I spoke too fast, but really I would like to leave the time to Nicolas and to your question and my answer. Thank you very much. Muchas gracias.
Thank you very much, Carmen.
Okay, I'm muting myself. I'm waiting for questions before your nice demo.
Muchas gracias, Carmine. Realmente bastante lo que se puede hacer con este sensor. Y hay unas diferencias claves entre lo que es un sensor de fuerza dinámica y una celda de carga. Y a continuación aquí tengo una... Perdón, vamos a hacerlo de otra manera. Aquí, voy a compartir mi pantalla. Viendo estos equipos se hace la pregunta de cómo puedo interactuar con ellos, cómo puedo acondicionarlos y usarlos en mis mediciones. Eh, Estos sensores de fuerza piezoeléctricos son compatibles con cualquier equipo que pueda leer un acelerómetro piezoeléctrico o con cualquier equipo que pueda medir voltaje si es que se usa el acondicionador correcto, que es un acondicionador ICP-IEP, incluido en equipos National Instrument como en NI9234 y en nuestros equipos de BESOS. Una manera de interactuar con estos sensores es usar entradas para acelerómetros tipo ACC, donde tenemos en realidad una gran variedad de cantidad de canales, cantidad de tipos de entradas, y podemos conectar directamente sensores de fuerza dinámica y, por ejemplo, sincronizar nuestra medición y tener al mismo tiempo que estamos midiendo aceleración, que estamos midiendo, por ejemplo, en un análisis modal, estamos realizando fuerza a través de un shaker y estamos midiendo la aceleración y estamos computando todo dentro de nuestro hardware y software de uso. O utilizar esto para monitorear procesos, monitorear niveles máximos de fuerza o también en pruebas de laboratorio tipo de vibración con control shakers o también pruebas de impacto. Todo dentro de esta misma solución a través de los equipos de procesos. Otra opción para interactuar con sensores de fuerza dinámica es el equipo digital de Modal, que como mencioné es un fabricante de sistemas dentro de Amphenol y compañero de PCB Piezotronics, que ofrece una solución más económica, compatible con USB, a través de USB con cualquier computador, cualquier teléfono, para leer sensores ICP, ya sea acelerómetros piezoeléctricos, micrófonos o estos sensores de fuerza que estamos viendo. Es como una de las maneras más también sencillas, en el sentido de que llegar y conectar, aunque una ventaja es que esto no incluye un software, es un poquito más abierto, por lo tanto, en realidad está pensado más para un uso como académico o para el desarrollo tal vez de soluciones propias, en sistemas basados a través de Python o MATLAB o LabVIEW. Dibusoft sí siempre va a incluir un software base con quien puedo exportar y puedo también integrar directamente variables como video, vibración o GPS, etc. Tengo a continuación una pequeña demostración dentro de Dibusoft. Y si me debería estar viéndose la cámara, pero tengo conectado en este equipo, tengo 4 entradas para sensores piezoeléctricos, las cuales tengo conectado un sensor de fuerza, con un filtro pasa alto de 0,1 Hz. Y este es un sensor de 500 libras de fuerza o de 2.200, 2.2 kilonewtons, sobre el cual tengo montado, que está montado sobre una celda de carga, con el mismo rango, también 2.2 kilonewtons. Esto tiene un filtro pasa alto de 1 kilo. En realidad, no nuestra frecuencia de interés para este sensor. En realidad, para esta celda, vamos a ver, sobre esta frecuencia, vamos a ver más bien ruido. Quiero hacerles notar aquí las especificaciones técnicas de este sensor. Puede medir hasta 2.2 kilonewtons, su peso es de 22 gramos. Si lo comparamos con la alternativa, con lo que pesa esta celda de carga, la cual estamos montado el sensor, la celda de carga pesa 2.9 kilos. O sea, el mismo rango, en 2 órdenes de magnitud de peso de diferencia. Aquí están las mediciones superpuestas. Esto sincronizado con video. Bueno, aquí tengo también otros sensores triaxiales y también para acoplar dos estructuras, force link sensors, y estos son triaxiales. Algo interesante que podemos ver inmediatamente aquí tengo aquí una forma de onda, una señal cruda, escalada al máximo o sea, con el factor de escalamiento correcto del sensor en el certificado. Estoy monitoreando sus valores máximos. Y aquí abajo tengo hay una cosa que es interesante ver aquí, es el nivel de ruido, el piso de ruido. Aquí la traza naranja es la celda de carga, y esto tiene un nivel de ruido inherente más alto que el sensor de fuerza. El piso de ruido del sensor de fuerza piezoeléctrico y su frecuencia útil son más altos. Es una señal que puede ser más limpia en ambientes donde tengo mala aislación o lazos de tierra. De hecho, aquí se pueden ver algunos pics en esa celda de carga en 50 Hz, ocasionalmente 57, 150 Hz armónicos eléctricos. De hecho, aquí hay algo que este filtro ayuda bastante a la señal de la celda de carga. Si lo subo a 3 kilos, mi piso de ruido debería aumentar. Se ve que sobresale la traza naranja, que es la de la celda de carga versus la del sensor de fuerza. ¿Dónde gana la celda de fuerza? La celda de carga es si yo genero una fuerza estática y la mantengo generando alrededor de 15 newtons en la celda de carga, y es una fuerza estática, está siendo medida directamente. Para el sensor de fuerza, su foco en este caso es medir cosas cíclicas, es medir impactos, es medir fuerzas en las cuales tengo contenido armónico, tengo contenido dinámico, y poder comparar esos valores. O sea, me refiero como, no necesariamente me interesa la parte estática. Y aquí podemos ver directamente el efecto de qué pasa con la parte estática del sensor. El sensor piezoeléctrico solamente está midiendo variaciones de fuerza. Ya que estoy manteniendo una fuerza constante, está midiendo cero. Una cosa interesante que puedo generar con esto es que lo que significa precargar es que tengo que someter al sensor a cierta fuerza para ponerlo en su rango de medición. Específicamente en este sensor viene precargado, así que no es necesario hacer esto, pero por ejemplo con este modelo y tengo que ejercer una fuerza específica durante la instalación. Pero poder ver la diferencia entre la capacidad de medir una señal dinámica y una señal estática es el propósito de esta demostración, y también poder aquí ver el nivel de ruido que beneficia al sensor de fuerza, el sensor de fuerza piezoeléctrico, que es especialmente útil, por ejemplo, en aplicaciones modales, donde estoy correlacionando esta entrada del sistema de fuerza con lo que sería, por ejemplo, la salida a través de vibración, sensores de aceleración o sensores de strain gauge conectados a la estructura. Pero es un sensor que tiene una salida más amplificada que una celda de carga, y puede también medir cosas más bajas. Y también el tema del peso. Estos dos equipos pueden tener el mismo rango de medición. Para aplicaciones dinámicas, este es mucho más compacto, es más fácil de instalar, más barato de instalar, hay menos cosas ¿cómo se dice? Menos cables que recuerdan. Este cuesta menos sensible al ruido. Bueno, para cerrar, volver aquí a la parte de DAX. Esto es un equipo Krypton dedicado con distintos canales para celdas de carga y sensores de fuerza. Realmente puedo conectar básicamente lo que sea. Y eso es como la demostración práctica para estos equipos. Y bueno, con eso quiero dejar abierta la opción para cualquier pregunta técnica, cualquier pregunta de alguna aplicación o de cualquier dobleza relacionada con esto o con cualquier sistema PCB o difusor. De nuevo, agradecerles su tiempo, su presencia, y eso, dejar abierta la opción de preguntas en cualquier idioma, que sea inglés o español. De nuevo, muchas gracias.
Hola, buenas, ¿se escucha?
Sí, sí.
Gracias por el seminario, el webinar. La pregunta que tengo es que trabajo haciendo ensayos de impacto o de drop test. Y la pregunta es si hay alguna forma con el sensor 208C05 de medir la energía.
Energía, esto implica área, ¿cierto? Esto implica un cálculo donde entra el área, ¿correcto?
Sí.
Sí. Carmine, para medir energía.
Nicholas, they want to measure the energy?
Sí, creo que tenemos un
Okay.
para eso.
Yes, an interesting application. We have a dedicated paper. It's not the short answer. So the only thing I can do, I can share my screen again. And I'll share where Nicolas will send you this presentation here. Hold on a second. Let me share my screen here. Can you see?
Yep.
Nicolas? Okay. Now, let me remember where I should take this one. The energy. Okay. Force should be somewhere. Here's force preload.
Creo que es, I think it's the drop and test paper.
Is automotive, yes.
Okay.
Is automotive. Hold on. Is in the automotive world. And yes, component durability, but not this one. Is in the white papers of force.
I think it's the one I shared. It's on the
Force. Yeah, this one. Anyway, one of these we show where to take this application, and I will send this paper, okay, to you, and you will see this how to measure the impact. Is exactly the one I showed you before, the impact drop test, okay. This paper there. Hold on. No. White papers. Okay. Now probably I can share. You will see during impact the force calculation and the energy. Okay, you can see now. Can you see?
Yep. We can see.
Can you see?
Este paper lo compartí en el chat por si acaso. Está para que lo vean directamente.
Can you see?
Yeah.
And the total energy, you can see acceleration. Drop test example is the one I showed you before. Okay. Can you see the energy in joule? Okay. Clear?
What do they need for this calculation? Is this just
well, to measure the force, and then they can go to calculate in this way. Okay. Just follow this paper. Of course, the sensor is different, but anyway, they will going to measure the force anyway. Okay. I will send this paper.
Sí, lo vamos a romper ahí. ¿Qué sensor están utilizando en este caso? El 208.
208 CO5, I understood. Right?
Sí, ese mismo, 208 C05.
Sí, sí, sí.
Este es el de mayor rango. Sí, ahí hay una fórmula, en realidad, básicamente no sé si es la forma matemática de calcular esto, pero también entiendo que aquí no está tomando en cuenta el área el área en la cual se aplica la energía. Pero te recomiendo en realidad revisar este paper, si quieres podemos ir revisarlo, te lo voy a mandar y puedes responderme y juntarnos a revisar cuál es tu setup de medición, pero este es un buen punto de partida para calcular esto usando este sensor.
Dale, muchas gracias.
Okay, thank you for your question.